we had this model, which we built up together, and which you extended with Wayne immunity, and now with super infection together. Wayne has his hand up.
Yeah, can you share the screen?
Yeah, thanks. So we have this model we built up together, and which you elaborated through. Now, I want to extend this model a little bit together in a way that will be interesting. Now, in order to do so, we're going to change some of the detailed assumptions just to work through some scenarios. But let's get in place some core elaborations of this, and then we can work out some details. Okay. So the first thing I'm going to do is I'm going to create a stock that's going to be called initial population. Okay, so we're going to call it initial population. Yes. Good question. Yes, let's do that. Let's do that. I think that's a great idea. Thank you. So I will have to. What I will do is I will post this this version of it, so you have that, so everyone can operate off of it if you had any trouble. And I'm going to okay, and then we can all work from a common base. Okay, so let's see. Here we go, and we're going to add it in. Models built-in class. Yeah, sure. I'll put it into the models built-in class because we'll post some successive elaborations of it. Okay. And mumble. Let's go grab this. Yeah. Okay. Good. So if you wanna grab it there, it's the last one listed. First SIRS version 2.5. Okay. So let's get going on this. We don't need this anymore. No, close it up. Okay. So first thing we're going to do is to add in a parameter that's going to be called initial population size. And this isn't perfect, but I just want to make it easy to change this in scenarios. So we're going to put in a population here of 200,000. Okay, so it's going to be here we go, 200,000. Okay, great. Okay, and this population is going to be everyone infective except for one. Everyone's susceptible except for one infective. So the number susceptible will be initial population size. Now, any logic will complain unless you put a link between them to indicate that it depends on it. Okay, it's a special sort of dependence. It's a dependence at the initial value, so it's a dotted one. Okay, and actually, we're going to make it. I said initial population size, but it will be initial population size -1 because we're going to start someone at in the infected state. So the initial value of the stock will be the population size -1. We're going to start someone, one single person infected. Okay. So build your model early and build often. So I'm going to make this. So we're gonna call this first SIRS healthcare or treatment, we'll call it treatment limited services or treatment limited recovery. There we go. V1. Okay. And I'm going to call it SD to indicate it's an SD one for myself. I have like hundreds of models, so just want to remember this. Okay, great. And in case you don't want to type that, I'll post it. I'll post it up and you can use my name. Okay. There we go. There we go. And it is posted. Okay. Okay, great. Next, we're going to focus on a situation where treatment is limited, or where recovery is limited by treatment. Meaning people have to be treated before they're recovered. So it's going to relate to this recoveries area of the model. Okay. And specifically, we're going to change it so that the number of people, how long someone is infected before they're treated, will depend on the availability of healthcare workers. Okay, great. So I'm going to now go and we're going to turn mean time infective. Right now, mean time infective is a parameter. It's a default value of 10, okay? And I'm instead going to change this to be a dynamic variable, a variable that has a some variable time depending on how many healthcare workers are available and how many people are waiting for treatment. The idea is if more people are waiting for treatment, and you get in the back of the line, you have to wait longer until you're treated. But if there's more healthcare workers to provide that treatment, you can proceed through that line quicker. Okay, that's a key idea here. Okay, so we're going to take mean time infective, and we're going to turn it into a dynamic variable. So I'm going to copy mean time infective here, and I'm going to delete it. Okay, and we're going to go make it a dynamic variable, and this dynamical variable is going to carry that same name, mean time infective. Okay, great. And initially, the value of this variable, this dynamic variable, will be given by a simple parameter. Okay. That parameter we're going to introduce here is going to be called time until seek care. Okay. Does anyone remember what the time units of this model are? Days. Yeah. Time unit of this model is days. I should say. Yeah. 5 days. It's going to be 5 days. Okay. Great. Okay. And we're going to connect that to mean time infected. Okay. Okay. Okay, great. Okay. Great. So mean time infective will be equal to, for now, time until seek care. Okay. So all we've done is kind of soup it up a bit. So we have a dynamic variable here, and ultimately it just depends on a parameter, but we're going to elaborate it now. What is the unit of time until seeking care? Right? Sorry? Yeah, days. So time until seek care is of dimension base. Okay. I can put it in brackets to indicate that I'm talking about a dimension. Okay. This is going to be important because we're going to be brief about dimensions. This will be called tau. I'm going to call this tau. Okay, time until seek care. Yes. Excuse me. I'm going to call this like the minimum. Say that again. As I said it to be given by the parameter. Okay, so now let's run this model. Let's go run it. Right now it's called simulation. Let's call it baseline. Okay, it can be a baseline simulation, and let's run this. Run this thing. Okay. Okay, so this is the same model you built up and that you elaborated, and it should have a familiar set of dynamics associated with it. Infection spreads. It reaches a peak here between 130, about 135,000. The number of infected comes down. The number of susceptibles drop, but then starts going up. Why is it going up? Why is the number of susceptibles going up? That's the drop. Yeah, well, it's not quite recovering it. Sorry? Yeah, loss of the immunity. So you see the number of susceptibles actually oscillates. It rises up, and the fact that we have a lot of susceptibles around allows what to happen? A secondary outbreak, right? And that rises up, that drains the number of susceptibles and sets the stage for a decline in the number of infectives, which lets the susceptibles rise. It improves towards an equilibrium where what is what's the case of this equilibrium? I asked you to view equilibria two different ways. What's one way? So what is the case at this equilibrium towards which it's approaching? What do we know is the case? How about for the number of people? How about for infected? What's the rate of change of infectives at this equilibrium? Anyone? 0, which means that what? In terms of flows, what? Inflows without flows means more specifically that what? The rate at which people are getting infected, people per day, equals the rate at which they're recovering, right? What does it mean in terms of a single individual? How many people do they infect before they recover? One single person. They're just replacing themselves. That's why that stock is not going up or going down. Does that make sense? Just rehearsing these concepts we've hit many times now. Okay, now that's great. Just reminding ourselves of the basic dynamics of this, okay? Okay, next. What I'm going to do now is we're going to elaborate this in an unusual direction. The idea will be, you still have to seek care. That's going to be a minimum time to get treatment. But there's going to be some wait you may have to undergo too. And that wait will depend on how many people are ahead of you in the queue. Okay. So we're going to have a characterization now of people awaiting care and then being treated. So I didn't plan this, but it's gonna have to be fun too, you know. And so we're gonna have infectives here, and then we're going to have some number of infectives come over to a state where they are awaiting care. So this transition is no longer, we're going to have infectives go to infectives waiting care. So these are infectives not seeking care. I'm going to change this to be infectives not yet seeking care. Wow, this is going to be fun. Okay, here we go. That's great. And this number of infectives not yet seeking care, we're going to have to fix it up in a couple places that refer to it. And then we're going to have a, yeah, this is going to be different than I anticipated, but what the heck. Okay, so then we're going to have a stock of infectives seeking care or infectives awaiting care, okay? Yeah, this will be fun. Infectives awaiting care, okay? Great, okay. Okay, and we're going to have people move from not yet seeking care to awaiting care with a mean time of time until seek care. So I'm going to disconnect this and I'm going to instead, and we're going to drag this out here. And I'll be sharing mine with you in just a minute. Okay, there we go. So we're going to have this go here. Okay, this is going to be cool. And there we go. Hey, come on. And there we go. Okay. Yeah. Okay. Okay. There we go. Okay. So these are infectives not yet seeking care. These are infectives awaiting care. And then we're going to have recoveries. And the recoveries will be occurring after a mean time to mean time until treatment. Okay, I'm calling it mean time until treatment. I'll provide you this in just a minute. So this one here is called seeking care now. Wow, this is a wild version of this. This is cool. Okay, so there we go. So people are going to be here until they seek care. How long will it be until they seek care? It'll be given by this time until seek care. It'll be a first order delay. There we go. Okay, that's cool. Look at that. And after that, they'll be awaiting care, and then they'll eventually recover when they're delivered care. And that will take some time based on how many people are in line ahead of them. Okay, so seeking care here, this is our first order delay. So what's the formula for this? Can anyone say? What's the formula for this? If this is a first order delay, we have a mean time until seek care and a certain number awaiting. What do we do? Yeah. So we do infectives not yet seeking care divided by time until seek care. Okay. So this is a classic first order delay, right? If this were a rate of moving forward, it would be infectives not yet seeking care concept hazard rate. But here it's a mean time. So the value of the flow is given by effective time of care divided by time of care. The units of this flow are what? If infectives is measured in people, what are the units of this flow? What does value of 10 mean? It means what? 10 people per day. It's a per day. It's people per day. Okay, great. So we have this being infectives not yet seeking care. And then this flow is instead, wait, come on, get back there. This flow is going to occur from here. Recoveries are going to occur from here. The new recoveries will be given by infectives awaiting care. Wow, this is going to be cool. Okay. Divided by that. Okay, so, and it's going to be mean time until treatment, not mean time infected. Time until treatment. Okay. And I'll pass this to you in just a minute because I kind of short this around a bit. Okay. Now, mean time until treatment will no longer be time until seeking care. We're going to have a formula for this. And I want to walk you through the reasoning here. And this is where some of the dimensional analysis comes in. Okay, here we go. Okay, so ladies and gentlemen, we're going to have some numbers of healthcare workers here. Okay, we're going to call them healthcare workers. Should be some number of them, and by default, we'll say that there are, let's say, 30 of them or 50 of them. Okay, 50 of them. There we go. There we go. Okay. 50 healthcare workers. Okay, so this was in days, the time until they seek care. We're going to have a mean time until treatment. Is that what it's called? Is that right? Treatment. Okay. And what is the units of this going to be? It's a time. What is it? Days. Okay. Anything else you can convert it, but that's fine. Okay. And now we're going to have a count of healthcare workers. I'll do these in different colors. That wouldn't be a bad idea. Okay. So we're going to have healthcare workers, and we're going to denote their unit as we're going to call it 8, right? And we're going to call the dimension of this one, we'll just call it T, to indicate a dimension of time. So we have dimensions and then we have units. Here, if we just focus on dimensions, T will indicate time. Okay. So time until seek care will be measured as it's a time. That means you measure in days, but time is sort of the semantic quantity associated with it. Similarly, time until treatment is time. Healthcare workers, the dimension of that will be 8. Okay. And we're going to have additionally, beyond that, a quantity of healthcare worker time, healthcare worker time per patient. Okay. Okay. Some number of healthcare workers, some number, and we have patients awaiting care. And there's going to be a time required per patient. Okay. Great. And the units of this, well, we're gonna need to mention that susceptibles, infectives, and the sort of subtypes of that and recovers are all dimension T. Okay. So healthcare worker time per patient is going to be the number of healthcare worker days, or healthcare worker time, which is healthcare workers times time divided by the number, the time per patient. So it's a unit, healthcare worker time, once you say times T per patient. So it's divided by T. Okay. So let's put that into our model. I'm going to put it into our model right now. Here we go. It's called healthcare worker time per patient. Healthcare worker time per patient. Okay, this is cool. This is cool. Great, great, ladies and gentlemen, great. Okay. Next, we are going to, so we have a number of healthcare workers, we have amount of healthcare worker time per patient, and we're going to say that each healthcare worker requires per patient 15 minutes. So that's 0.25 divided by 24.0. So that's 15 minutes. In other words, it's 1/4 of an hour, which is 1/24. I could have phrased this in any number of different ways. I could have said 1 divided by 1.0 divided by 24 times, times 0.25 or whatever. But it's 0.25 divided by 24. So it's 1/4 of an hour. 1/24 would be an hour. You got that? Huh? Okay. Great. Okay. So the mean time until treatment is going to depend how many people are awaiting care, how many healthcare workers there are, and how much healthcare worker time there is per patient. And the question is, what is the formula for this going to be? Let's go think about that. Okay, here we go. Here we go. Okay. Mean time until treatment for the people awaiting care. Well, you tell me. Suppose we have 8 healthcare workers. Suppose we have some count of, so suppose we have a certain number of healthcare workers. I'll call it, to denote it kind of in brief terms, I'll indicate, I'll indicate that variable as, I'll indicate that parameter as lowercase h. Healthcare worker time per patient, I'll indicate that as, let's say, yeah, maybe I'll call it rho, Greek letter rho, great. And then I'm going to say we have a certain number of people awaiting care. These are people awaiting care, and I'll call them, let's see, W for people waiting. So this is people waiting. Okay, people waiting for care. People waiting for care. That's that stock. Waiting for care. It's maybe I'll give it the name that's actually in the model. It's called infectives awaiting care. Infectives awaiting care. There we go. Okay. We'll call it W. So if you have this many people awaiting care, you have 8 healthcare workers, and it takes each healthcare worker a certain amount of time given by rho to treat each patient. How long will it take for the patients to get care? So you have W people awaiting care. You have W people awaiting care, and each of them will be needed to be treated by a healthcare worker, right? So let's start reasoning this through in terms of the dimensions. We're going to be arriving at something here, which will be the mean time until treatment. What are the units of that going to be, or what are the dimensions of that going to be? This is a what? Time. This is a time. We've got to get out something that's a time. Okay. Okay. Now, let's think through what we have as our building blocks. We have W, we have rho, and we have, I'll put this in green. W, and we have H as our building blocks. H. Okay. So this is going to be W, and this is going to be H. Okay. There are building blocks. So let's think about it. If we have more people waiting in line, is it going to take a given person longer or more or less time to get care? More. Okay, good. So we might think W is probably in the numerator. If we have more healthcare workers to treat those people, suppose we have one healthcare worker versus suppose we have 100. If we have 100, do we get treated quicker or does it take longer to get treated? Does it take more or less time to get treated? Less. Okay, so probably that's in the denominator right here. And then if this healthcare worker time required per patient is more, so if it requires them an hour to treat each patient compared to 15 minutes, the longer it requires them to take to treat each patient, will it take each patient then longer to get treated or shorter? Longer, yeah. So right. Okay, so a plausible candidate here that we might think about is W, the number of infectives waiting care, times rho divided by H. And let's think about the units here. The units of W are people. So I call that P, P. So the units of this are people times, and what are the units of the denominator here? H, healthcare workers. And what are the units of rho here? H times T over P, right? So the units of rho are H times T over P. So what are the units of this overall expression then? Anyone? T. Right. So this H cancels with that H, right? This P cancels that P, and we're left with T, right? That makes sense, right? We have a certain number of healthcare workers. It takes a certain amount of healthcare worker time per patient. And then we have a number of patients. And so if you multiply them like this, the numerator here, W times rho, is the total number of healthcare worker days required. And if you have healthcare worker, if you have this many healthcare workers, H, you can treat them in a shorter time. You can treat them at a quicker way in fewer days. So if we have 100 healthcare worker days of time needed, because the number of infectives awaiting care times the healthcare worker days required per patient is 100, and we have 100 healthcare workers, it will take a day that you have to wait in line. Does that make sense? Okay, so this is what we want to put in place here. A bit of dimensional reasoning. I expect you'd be able to reason through things like that. Dimensions are incredibly useful, and they're unfortunately under-tapped in computer science. Okay, so we're going to take this mean time until treatment, and we're going to transliterate this expression, right? So in the numerator of the expression are infectives awaiting care. That is infectives awaiting care, great, times here healthcare worker time per patient, that's rho, divided by healthcare workers. And that should be in lowercase. I don't know why I put it in uppercase, but I'm going to put it in lowercase here. And now I'm not taking advantage of any logic's rather nice functionality of refactoring by allowing it to automatically rename things for you, but there we go. Okay, now it's giving me an error here, so let's go see what's okay. Yeah, so there's a couple of things that have to be cleaned up here. Okay, number one, something's referring to infective. I bet it's this. Okay, yeah, so it's the total population. So the total population needs to now sum up. What do we have to add to the total population now? Anyone? Anyone? Yeah. So the total population now is no longer just infective. It's infectives not yet seeking care. Come on, seeking care plus infectives awaiting care, right? Awaiting care. Okay. It's still complaining. So what is it complaining about? It says is not used, but it's expected. Okay, so why is it an unhappy camper here? Because I misspelled it. That's why. Yeah. Okay. Now, is this a phantom error or is it happy? Yeah. Okay, it's happy. Okay. Infectives not yet seeking care is not used but affected. Okay. So what do we have to do here? Anyone? What do we have to do here? We want to compute the fractional prevalence of people in the population for infected. How do we have to fix up that? Yeah. Okay. You got it. You have to sum up the infectives. So here we go. So we're going to have a total infectives, right? Okay, great. And we're going to have total infectives from each of these. That's great. Excellent. Total infectives. And so we're going to have infectives not yet seeking care plus what? What's the other part? Infectives awaiting care, right? Okay. And then we have to use this total infectives in fractional prevalence instead of its old just referring to infectives, right? Okay. Total infectives. That's everyone. Okay. So it says infectives not yet seeking care is not used but is expected. Okay, yeah. So we no longer need this one because it's all factored through this one here. This one totals up the two infectives, and then we just refer to that. Okay, that's great. Okay. Not until I'm done with it. Not until it compiles. There's no way I'm going to post it until it compiles. Okay, and then over in this graph here, I'm going to have a total number of infectives. Right now, it just has a total number of infectives label, but I'm going to say infectives not yet seeking care. Okay, and then I'm going to add another one, which will be infectives awaiting care, and this will be infectives awaiting care, and then finally there will be total infectives, and I'm going to make that equal to the count of total infectives. Total infectives. Okay, great. Okay, so we are now in a fine situation. I want to add one more graph, and then we'll be able to start using this model. So I'm going to add another graph here, and I just copied this graph, pasted it here. I'm going to get rid of most of these things and only plot out one. I'm only going to plot out how long people are waiting, okay, which is given by mean time until treatment. There we go. Mean time until treatment. Okay, there we go. Okay, great. Okay. Okay, so here we go, ladies and gentlemen. Let's make sure it builds. Let's make sure it runs. And we can then start to experiment with it. So how do you think having some time required until they seek care will affect the dynamics of this model? And how do you think this generally? Oh, okay. So wait, we have a problem here. It says not a number, new recoveries. What's new recoveries? It says that's not a number. Okay, so let's go see what's going on. Do we have an initial value here? Yes, the initial value of that is 0, 0. Okay, great. So we're going to try to figure out why is it getting not a number values, okay? Great, and time until seek care is 5, and this value is that. So I don't see anything obviously wrong, but let us go and see where this problem originated in the model here. Okay. Okay, so this is complete. Mean time to treatment is 0. Why is mean time until treatment 0? Because nobody is infected care. Okay. Okay, that's fine. So there is a construct in any logic and commonly in system dynamics called ZIDZ. Okay, and it basically means divide one thing by another, except if the denominator is 0, in which case make it 0. In this case, if the number of infectives is 0, and awaiting care is 0, the mean time until treatment will also be mean time until treatment will also be 0. So both the numerator and denominator will be 0 at the same time. So we're going to do ZIDZ, which will be basically saying if this is 0, then use 0 for the entire value. Okay. Because both the numerator and the denominator will be 0. There'll be nobody awaiting care, but there's nobody and they would be, oh my gosh, look at that. Oh my gosh. That's really exciting. Okay. So let's go see what happened here. And we're going to see if we can figure out. Okay, so something bad has happened. Mean time until treatment is negative. This is not good. Okay, total infectives is negative. Infectives not yet seeking care. Okay, so this is fascinating. What is going on here? Okay, so we put in place this new recoveries. Okay, so we have the idea is that we have infectives awaiting care divided by this. I don't see a problem with that. Time until seek care, I don't see a problem with this because we just have this divided by that. Yeah, okay, so I don't see an issue here, okay. And the healthcare worker time per patient, yeah, wow. So I'm trying to figure out what's going on. Well, you'll get to see me try to figure it out. Okay, so I'm going to I'm going to go here and I'm going to run this model one event here. And I am going to switch to the model. Great. Okay, let's go see what's going on here. Okay, at the initial time, we have 0 mean time to treatment. We have 0 recoveries. Okay, that all looks fine. We have some number of new infections per day. That also looks great. Okay, so what's happening? Wait, any thoughts? Okay. my hypothesis is mean time is 0. It is, but I put a ZIDZ there, right? Oh, I thought you put ZIDZ. No, I put on new recoveries. Okay. So that's not correct. No, but it looks like mean time of treatment is what I would say. No, I didn't, because I figured number of healthcare workers will always keep as positive. I think it's the limiting behavior. So in other words, when there's almost no one in fact awaiting treatment, and they get treated extremely quickly. Okay, well, such is the price of innovation. We're going to say here that, okay, this is ugly, but it will do. For mean time until treatment, I'm going to say that it can be no shorter than what should we say? Say no shorter than the healthcare worker time per patient. Yeah. So at least it has to be the amount of time you spend with a healthcare worker. So I'm going to say the maximum of healthcare worker time per patient and this thing. So the idea is that, look, even if there's nobody waiting, even if you're the only person, you're still going to wait for at least this amount of time here. So it's the maximum of this. If this is greater than this, then you'll still wait that time. By contrast, if this is greater than this, you'll have to wait all this time. Okay. And again, I haven't forgotten, I'm going to post it, but I don't want to post it while it's still having problems here. So here we go. And there we go. And it's a thing of beauty and a joy forever. Well, maybe not, but okay. So now we see this rising up, the number of people who are infected. It rises up and it reaches a plateau. You notice this is the mean time until treatment. What is this telling us in terms of mean time until treatment? Do you remember the minimum time until treatment is this healthcare worker time per patient, 0.01. So you can see this really escalated. Why did it go up so much? Can anyone say? Why do you think that rose so much? Yeah. Yeah, people are waiting care. And so that makes others who are waiting wait longer. And while they're waiting, what are they doing? Spreading the infection. So they can't get treated, they can't recover until they're treated. And until they're treated, until they recover, they're going to be contributing to this total infectives and the fractional prevalence and spreading it, right? So here we have an infection that is spreading to considerable levels, partly driven by the waiting time. Now, we continue to run it on. There's this large initial outbreak here. And now we see it going and approaching, once again, an equilibrium. Notice the mean time until treatment now is very, very small, right? Do you see that? Okay, I'm going to post this and allow you to work on it, but we're going to be experimenting with this here. Okay, we're going to add some scenarios. Okay, and there we go. And this is it. Yeah, okay, fine. Oh, you know what? I should change the name. Okay, fine. Okay, save as version 2. great. So, good. And, okay, great. So you should be able to get this, it's version 2. Okay. So ladies and gentlemen, when we observe this running, what we're going to see is that in this initial phase, people get infected at very large numbers. And because they get infected at very large numbers, the time until they can be treated is much higher, which allows the number of infectives to remain elevated for a while. Okay, you'll notice that the number of infectives not yet seeking care has a rather sharp increase. But what is this telling us? What's the yellow curve telling us? This is infected awaiting care. What is that telling us? All right. A large number of people are awaiting care even after the initial outbreak has died down in terms of immediate spread. They're awaiting care. They got it a long time ago and they're awaiting care, and therefore they're continuing to spread it. The total number of infectives is large as well. Yes, Ardalan.
Maybe there are there are some we all report, but we still have to put them involved.
Well, yeah, but in this case, they're actually infective. So it's infective long term. There, it's like they have a long term STI or something like gonorrhea or chlamydia. So it's staying within their system. Okay, so we see here in the initial phase up here, a large mean time until treatment that keeps them infected for longer, and then you see it going to an endemic equilibrium. Let's put in place some experiments. We're going to take this baseline. We're going to put in place an experiment where we have a lot fewer initial healthcare workers. Okay, so we're going to say initial healthcare workers. We're going to put in place a far smaller number. Let's suppose we say initial healthcare workers 1. Okay, and all we're going to change from the baseline assumption is we're going to assume there's only 1 healthcare worker rather than 50. How do you think this will change? Yeah, there it is. It won't go down nearly as fast because why? Because they have to wait longer for care, right? The number of healthcare workers, if this is 50 in the denominator, this is much smaller than this is 1 in the denominator. So Harriet prognosticated that the number of healthcare workers remain higher. So here's the number of healthcare workers awaiting care. What's going on here? How many people are there in the population total? 200,000, right? Just about everyone is infected, right? This is highly dependent on the amount of healthcare workers that are available. And this is going up to a very, very high level. If we run this forward, we'll see it's actually staying at a high level. I'm going to change the time for this to go for not just 2 years, but 10. We'll change it for 20 years, so 10 times that, not 730, but 7,300. Okay, 7,300. Let's just go watch what's going on over this longer time frame. So it's going up, and it's remaining quite high. Right? So it's gotten into the state of a very high endemic equilibrium. Now, when we had 50 healthcare workers, was there an endemic equilibrium? Was the infection staying around? It was. Remember when in the cycles and then it approached equilibrium? Here, the equilibrium is vastly larger, right? It's like over 160,000 of the 200,000, over 80% of the population is infected. Right? Okay, so now let's I'm going to do another experiment here, or I'm going to run this experiment. I'm going to start it running, and we'll go out until after it's reached this very high level here. Okay. And I'm going out to about a year. So roughly speaking, about here it's 400 days, fine. You'll notice the number of the total infectives is very, very high here. It's again around 180,000. Now I'm going to impose now a larger number of healthcare workers. I'm going to say, suppose now we have 5 healthcare workers. Okay. 5 healthcare workers who are present. How do you think that will affect things if we have 5 healthcare workers? Yes, fine. Okay, so we'll have a drop in the number of infections and a drop relatedly in the number and the amount of time they're waiting. Why is the amount of time they're waiting going down? Well, we have more healthcare workers to work through the number of people have to be treated, right? So you're not waiting for treatment to get cured of your infection for as long. You're getting to the, once you're in line, you're getting to the front of the T500 cell, right? As if there were one healthcare. Okay, and this lowers this prevalence down to the number of healthcare workers being increased, lowers the number of people that remain infected to a far smaller value, right? It lowers it down to about 20,000. Okay. Okay, so here, having those healthcare workers in place allowed you to achieve a very, very high increase in how quickly people are treated. Okay. Let's suppose that we had put those healthcare workers in place from the start. So we said initial healthcare workers 1, and we changed it dynamically. We changed it while it was running here. Let's go and set initial healthcare workers to be equal to 5 here. Okay. Okay, and we're going to have 5 of them from the start, from the get-go. Okay. Here we go. And we're going to run it here. And once again, we're going to see that, well, people get infected. There's a lot of people waiting for a long time, but it ends up coming down to kind of a similar value. Okay. We have these 2 different modes depending on the number of healthcare workers there are. I talked last time about a notion of basins of attraction here, where we have here a number of susceptibles on a state space plot, and here a number of infectives. And I've spoken about how you can get cases where there's different equilibrium, like one with here, if we were to think about it in terms of susceptibles and infectives, one might be a large number of infectives, but few susceptibles, maybe up here, and another endemic equilibrium perhaps where you have many more susceptibles and fewer infectives. And here, what we're seeing is healthcare workers. The number of healthcare workers might place the system into a situation with a lot more infectives, fewer susceptibles, and a lot, or alternatively, if we have enough, a lot more susceptibles and fewer infectives. Let's try looking at this some more though. So we have this model which can get in kind of these very different modes. We're going to imagine now, imagine the time until seeking care is somewhat smaller. So here we have a baseline. We have a time until seek care of 5, contacts per person per day of 20, and a probability per discordant contact to transmission of 0.1. Can anyone tell me what's the basic reproductive number of this model? Anyone? Yeah. 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 Good. Time until seek care. Yeah, and then there's actually a little bit of extra time required to see the healthcare worker. There's a minimum of time we have. Okay, so that's right, and it's going to be upwards of 10. If we were to change this here to instead get in place, and I'm going to put this down here, time until seek care, that's smaller. And actually, before I do this, I'm going to change this to a much lower risk of transmission. So 20 times 5 is 100 times 0.1 would be a basic reproductive number of roughly somewhere over 10 because of the additional time that is required. I'm going to change this down. Instead of being 10, I'm going to 0.1, I'm going to make it 0.0133, and I'm going to call this reproductive number. I'm going to call it 3. It's roughly 3. Okay. So this is going to be a lower reproductive number. Maybe I'll just call it low reproductive number. I'll post this here in a second. Okay. We're just about done here. Okay. And I'm going to run this. So here we have a quite low reproductive number. We would get an initial outbreak here, and you notice that it rises up here. The number of susceptibles rises up. Then it declines here. You'll notice that as it's rising up, after this, we don't really have a lot of people awaiting care. It's only for that initial outbreak we have a large number of people awaiting care here. It's not large enough to tax this system after the initial outbreak. And as a result, it ends up going to an equilibrium that is not really too strongly affected subsequently by the number of healthcare workers that are available after that initial time. Okay, I think this is all we have time for today. What I wanted you to remember from this is that you can get the same system into very different equilibria with different characteristics. In one case, an infection that remains at very, very high levels not even cycling, but just approaching that equilibrium on the one hand versus one which has a cyclic type behavior approaching the equilibrium. You can have this, and changes in model assumptions, such as the number of healthcare workers mediating care, can shift it from one equilibrium to another. Okay, one endemic equilibrium to another. Both of these are stable. Both of them are, once they get established, they resist change, but they're at very different points qualitatively. One, a level where it's very, very high number of infections, and one where it's comparatively low, but it cycles to the equilibrium at a lower level of prevalence. I also wanted you to carry away some understanding of this dimensional analysis involved, where we're assigning dimensions to particular parameters and reasoning about what a formula must be to make sense, and checking it dimensionally by saying, does this formula make sense? Okay, that's what we're doing here. And I want you to be able to carry away a sense of how to do that for a formula, how to compute its dimensions based on the dimensions of the quantities used in that formula. Okay, that's all we have time for today. Thanks very much, and I'll post this model here. Hey, questions? Yeah.
Last time we discussed about turning some of one of the variables endogenous.
Right.
I ran into some problems with it. So I was because we did the with alpha as a south.
Yeah.
I forgot the scripture right now. The problem is defining alpha, what alpha should be,
Right.
the values for it. So it was conflicting a little bit. With the time available, I think it's gonna be a
Yeah, so maybe don't do that. Just but note that you explored this. There were some issues with it. And keep your report. You don't have to go into it for your report.
okay there. Yeah, and that was one thing. Oh, about the report, do you have any examples with the formatting or something?
Oh, yeah.
like that?
Yeah. Yes, I do.
What I'm running into problem is not what to write, but how, like the structure.
Sure. Okay. I could send you one or two example reports. If that would be helpful. Okay. Just they'll be from past years, so just keep them confidential, and I can pass them. Yeah. I mean, generally speaking, like the report is often going to include a description of the model structure, a description, well, a little bit of background, motivation, etc. Bit of discussion of model structure, bit of discussion of model scenarios. And then maybe some discussion actually before that of model assumptions, so they'll often that goes along with the scenarios. And then some discussion of the model results.
The results.
Sort of outcomes in the model. Yeah.
You think it's valid to put like developments or things to be considered?
Oh yeah, absolutely. Yeah. Sort of priorities for extensions or future work or possible directions that this could go if there were more time, etc. I mean, that's actually quite nice to share. So yeah.
I think that's where I will.
Yeah, talk about that.
Yeah.
Okay, cool.
That's it.
Okay, cool.
Probably I am. Monday or Sunday or.
Sounds good. Yeah.
In terms of writing, I did a lot with formatting, just backing down.
Right. Okay.
So
So yeah, I
putting the block together.
I think, often it will help to describe the model to have images too. So I would include them.
Images, and for the data also get images of the plots.
Of
The pockets, like the graphs.
oh, you mean like for the output?
Yes.
Like for the scenario results? Yes, that would be part of the results section. Yeah. Yeah, so it would include findings there. I mean, including some description of sensitivity analyses, what if analyses you did would presumably be part of the scenarios. Yeah. Okay.
Thank you.
Okay, very good. Yeah. Yes, Rashid. Hi.
I did this way. I don't know.
Yeah, see, but here's the thing. So it's a good start to think. But here's the thing, because cumulative infections does not drain down the number of susceptible. So like the occurrence of infection will bring someone from a susceptible state to an infective state. But having here, the recording of cumulative infections, that doesn't change people's health state.
Right.
It's just a recording of it.
Right.
And so you just want it, you don't want it to drain a stock. Remember, within system dynamics models, a stock needn't come from, a flow needn't come from another stock. A flow could come from a cloud, exactly. Now, I see. So here, you're basically probably just computing the same thing that's computed there. And that's okay. There's no problem with that, except that you can just, since it's already computed there, you could just use it there. You see what I mean?
Yeah.
Yeah, okay. Okay. Okay, good luck. Yeah. Yeah. Oh, yeah. Yeah.
About, we discussed about the research.
Yes, for the summer. Yeah, so I'm awaiting news on a big amount of funding right now. And
We talked about it.
it's any day I'm supposed to get this. This was this one I gave the talk
Yeah.
2 weeks ago, and like it's renewal of funding, and the funding that's to be renewed expires tomorrow. So I need to know, is it going to be renewed?
Or not.
And that was the whole point of that presentation 2 weeks ago, et cetera. Now, they seemed, and I'm told internally that they were very happy with it, but I'm just looking for firm understanding, if the funding is renewed, because if it is, I have a lot more latitude. And the possibilities are much larger. I still think there's an additional colleague of mine who Wade knows really well, who particularly works on the health economics side. And I'm thinking, if this funding is not renewed, particularly I may reach out to her and say, would there be an interest in you helping out with some of her possible scenarios? Period. I think that this needs to be pushed back